Okay, hey. I got distracted for a minute, but I'm back. Here comes part two of the quiz review for, I guess, what's now Friday. But here we go. I'm going to start on sheet number one, of course, CA number one for the quotient rule. And again, I said I'm not going to do the odds because you've already got the print version of the answer key for the odds. So we're going to go ahead and start with the evens. So we'll start with two. This guy here. Make a bunch of room. And we'll hop to it. All right, so now that we're doing quotient rule, as we look at this guy, we should see, that's weird looking. We should see that we've got this factor in the numerator, we've got this other factor in the denominator. I could sort of make life easier for myself. It's probably not really worth it, but you could factor out a 5 halves, like the coefficient here and the 2 here, and then you could kind of do the derivative, the ddx, on just an e to the x and a sine x. But that's essentially what you're doing anyway. So I don't think it's worth it to even bother thinking about that, but I don't know, maybe we will. That's what's happening. You know what? Sure, let's do that. So we're now finding g prime. And g prime would be 5 halves times the derivative of just the e to the x and the sine x. We can essentially ignore the 5 over 2 is what I'm saying. So we get 5 over 2. Then quotient rule kicks in, and we want to do the derivative of the numerator. So that stays e to the x. Multiply that by the denominator. That's a sine of x. Then you subtract the numerator, which of course is still e to the x because I'm not differentiating this time. I differentiate the numerator the first time, leave the denominator alone. Then the second time through, we do not differentiate the numerator, but we do differentiate the denominator. So derivative of sine gives us a cosine. Whoops. So e cosine x. And then, of course, remember, you now get the denominator squared. So sine squared. All right, and then looking at this, if we're going to clean this up, then I see an e to the x that I can factor out to just be left with sine x minus cosine x. And I'll put that all over sine squared. And then we've got this factor of 5 over 2, which at this point, I guess we just kind of reattach everything. The factor of 5 would go into the numerator, just become a coefficient on the 5e to the x. The 2 would go here, just become a coefficient on the sine. But I think that's the end of the road for us. We can't simplify that any further, so that's that. And that's 2. Let's try 4. So here's 4. Make it a little bigger. Actually, just get rid of everything else. And here's 4. Again, here we've got a bit of a choice to make. Like, we could certainly just go right at this problem and do the derivative of the top, derivative of the bottom, all that, do the whole thing. But since these are just polynomials, there's really no reason for me not to maybe clean this up and just do the first term for x cubed divided by the x squared, then the second term, 5x squared divided by x squared, then the last term, the plus 5x divided by x squared. I actually can get away with doing this problem without ever doing the quotient rule because here these x's cancel with those two x's, so now you just have 4x. That's obviously easy to differentiate. Even easier, these x's cancel, you just get 5, so that guy's derivative is 0. Then here, technically this x cancels one of those x's, so I still have an x on the bottom, but I could rewrite that as 5x to the negative 1. And so now I have g of x expressed in such a way that I don't need quotient rule anymore. And this is totally fine unless, if my directions completely say, find g prime using the quotient rule, then of course you wouldn't be allowed to simplify to try to avoid the quotient rule. But I don't think my instructions will say that. I think I'm just going to say, find the derivative using the method of your choice. And then what I'll do is I'll make sure there's some functions in there where you have to use the quotient rule, but this wouldn't necessarily be one So if you wanted to kind of simplify first and then start to try to do the derivative by by just power rule, then more power to you. So speaking of, now that we're in this form, we're just going to do the derivative of that guy, do the derivative of that guy, do the derivative of that guy, and it's pretty simple. So the derivative here is 4, the derivative here is 0, and the derivative here is negative 5x to the negative 2. That's it. That's my derivative. Just cleaned it up now. So this 4 is a 4 for a minute. This will be minus a 5 over an x squared, because you got to kick those negative powers to the bottom. And then I'd want to combine these. So that would mean you'd want to multiply this 4 by an x squared over an x squared. So now you've got that common denominator. And then you could give me an answer of 4x squared minus 5 all over x squared. And that's it. Now if we had done the quotient rule here, it would have been a lot more steps. We would have had to differentiate that and that and that, multiply by that. Would have had a denominator that was x squared squared. And so we're kind of dodging a lot of bullets here, where if we had done that, we would have had a whole mess of terms in the numerator. And I think a bunch would just kind of cancel out, but still it would be more than we cared to. Then we'd have a factor of x squared that would cancel out, so that our x squared squared, which is x to the 4th, would be able to cancel part of that to just be left with the x squared. But if you were to try it out, you'll find that simplifying g of x first is a far more efficient way to go, so I highly recommend it. All right, let's do 6, and here's 6. And again, I'll just take a picture of it and throw the rest in the trash. All right, and looking here, this time I don't really see a way to rewrite this, because I can't just divide each term. I guess I should point out, the reason why this was so easy to rewrite is because the denominator was a monomial. You just had the 1x squared, right? So everything just kind of divided, cleaned up easily. Over here, if you were going to do the same kind of thing, you could technically, but you'd get x over x squared plus 2, the whole denominator, plus 2 over x squared plus 2. And all you've done now is you've made yourself two terms whose derivatives both require the quotient rule. So you've only made it worse. And these things don't clean up. So you can see why that approach this time is terrible. So don't do that approach. Instead, just get in there and do the quotient rule like you know you're supposed to. So f prime of x is going to be derivative of the numerator, which is just the derivative of x plus the derivative of 2, which would just be 1 plus 0. The whole derivative just 1. And then times the denominator, x squared plus 2. Then you'll subtract from that the numerator, x plus 2, times the derivative of the denominator, which will be 2x plus 0, so just 2x. And that'll be all over x squared plus 2 squared. Okay, clean this up. I don't think we can do a ton to it, but we can definitely clean up the numerator. Obviously multiplying by 1 doesn't really do anything, so we just get our x squared plus 2. Now here I'm distributing a 2x, and I'm going to go ahead and distribute a negative onto that at the same time. So we're going to get a negative x times a 2x will be a negative 2x squared. Then we'll have a minus 2 times a 2 will be a minus 4x. That's my numerator. Denominator stays the same. X squared plus 2 squared. And again, we're not going to expand that out because that's not going to get us anywhere, so there's no point. Alright, now I got a quadratic term and a quadratic term, so those combine to make negative x squared. Then I've got my one lone linear term, so we'll just bring that down, minus 4x. Then we've got our one lone constant, we'll bring that down, plus 2. And this is all over x squared plus 2 squared. Alright, in the numerator, I can factor out a negative, so I'll certainly do that. and I'll factor the negative just all the way out in front of the fraction. That's where I like it. If you know me, you know that that's how I like it. So that's an x squared plus 4x minus 2. And then an x squared plus 2 all squared. And again, if the numerator was factorable, you'd have to factor it, but you're not going to find factors of 2 that add up to 4. So we can rest pretty sure that this thing does not factor. And expanding my denominator wouldn't help me cancel anything, because if I did expand this, let's just do it. For anyone who doesn't really know why I've been telling you not to bother expanding, well, expand it then, and maybe you'll see. If you expand it, you get x to the 4th. Then you get 2x squared and another 2x squared, so you get a 4x squared in the middle. Then 2 squared is giving you a 4. But again, what do we have? We now just have 3 separate terms. And in the numerator, we have 3 separate terms. And as I hope I've said a bazillion times, you can't cancel out terms. It's not like this 4 can cancel with that 4. These 4s are connected to other stuff. You can't cancel them. You can't cancel this x squared for the same reason. So expanding these factors isn't useful, because you don't end up with stuff that you can cancel. Now, sometimes you do, but I pointed out when we do. It doesn't happen when you have polynomials like this. It happened in a different setting. And we could talk about that tomorrow. But anyway, let's rewind. This is where we ought to be. We cannot do any better than this. So throw a box around it. And that's 6. Let's go to 8. All right, 8 is another one of these which I can't get enough of. All right, so let's make room. Get rid of b. We'll do b later. And so we're going to do these the same way we did the last ones. I would still say that your first step is to go ahead and find h prime in general. So find me h prime of x. Don't do any substituting yet, just actually do the problem. Now this 2 again means that if you wanted to, you could kind of pop out a 2 and then imagine doing the derivative d dx of just the j over the k. So by popping out that 2, I guess we could maybe more clearly just visualize how quotient rule works. It's just kind of straight up normal quotient rule. So we'll have this 2, and then quotient rule says do the derivative of j, multiply it by k, then subtract from that j times the derivative of k, then divide that whole mess by k squared. Okay, so this is fine. You don't have to try to simplify that or anything. You could stop there. But at this point now, we switch over to trying to find h prime of -1 specifically, which just means plugging in -1 for all these. And honestly, I think I'm fine with you just going ahead and substituting in directly. So hopefully it's clear that what we've got here is, in the numerator, it's a thing times a thing. Something times something else. Then we're going to subtract something times something else. Then in the denominator, we're going to divide by something that's getting squared. So what are all those somethings? Well, j prime of -1 is this guy right here. Plop a -4 to that position. And then k of -1, normal k, not k prime, normal k, that's 5. Then j is giving 6, k prime is giving -6, and k again is giving 5. So here we are. We're just looking at a 2 that's multiplying a -20, technically minus -36, dividing it all by 25. So that's beginning to look a lot like a 2 times -20 plus 36, so positive 16 over 25, which now, if we're multiplying, put the 2 over 1, and we see that the 2 will multiply the numerator only, so that'll go to 32. Denominator stays 25, so 32/25 should be the answer, but we'll go and see if that's truly true, and lo and behold, it's true, 32/25. All right, so that was 8, and I'll do part B for you now. Okay, so if we're doing B, then I'll put B right there, and I'll white out all the rest of this stuff, make us some room. But these problems are all really similar to the ones that we did when we were doing the product rule. You want to think about these in exactly the same way. So if I've got this function here, then I could rewrite it a little bit, sort of, but it's basically the numerator is 1 minus k of x. I can't do anything with that. It just is what it is. My denominator, I could factor out. Doesn't really help to do so. So maybe what I'll do is just rewrite the j with a 1/2 coefficient. And that, I don't know, that sort of feels a little better to me to have it like this. But it ain't great. Okay, let's differentiate. F prime, again, just straight up do quotient rule here. We've got a numerator, that's orange. We've got a denominator, that's lavender. So following our little pattern, we do want the derivative of the numerator. By the way, to do the derivative, you're going to do the derivative of the first term. The derivative of 1 is 0, so I guess ignore it. Then the derivative of k would be k prime, but it is 0 minus k prime, so it is negative k prime. Okay, now we multiply that by the denominator, the lavender stuff, and don't differentiate, just multiply. So it'll be 1/2 of normal plain old j of x minus 4. Then we'll subtract. This time we're bringing down the orange numerator, 1 minus k. But we're multiplying by the derivative of the denominator. So that's going to be 1/2 times j prime. But again, we'll do the derivative of 4, and that'll just be 0. So we've got a minus 0 here, but there's no point in showing that, so don't bother. Then downstairs, we'll have that entire lavender thing, but squared. So it'll be 1/2 of j of x minus 4, and then whatever the heck that turns out to be, when all is said and done, you'll square it. Okay, so there's my derivative in general. Now that I've done it in general, I can substitute in and figure out what f of -1 is. And again, k prime of -1 is 6, but it'll be negative 6. I'm going to go ahead and just show that. We'll clean it up in the next step. But this is negative 6. It's going to be a positive 6. So now I have 1/2 times j, which is 6, minus 4. Minus sign, 1 minus k, which is 5. Then 1/2 of j prime, which is -4. Then I got a denominator where I've got 1/2. Well, isn't it just this guy again? Yeah, it's the guy from right above, right? So it'll be the 1/2 of the 6 minus the 4. But square the whole thing. And then from here, there's nothing left to do but a couple of rudimentary calculations. So this is going to be a 6. 1/2 of 6 is 3. Take away 4 is -1. Then I'm subtracting a -4 times a -2. And this whole mess will be divided by a 3 take away a 4, which is a -1 that's getting squared. So this looks an awful lot like a -6 minus an 8, just divided by a 1, because -1 squared is 1. So that looks like -14. But I always feel like it's super easy to make a mistake somewhere, so let's go see if that's really right. And of course it is. -14 is right. And that'll do it. That'll be the first quotient rule worksheet. So let's go to the second quotient rule worksheet. Right here. And I said I would do the evens only, so we'll do 2 and move on. All right, give me that function. And I don't want any of the rest of that, so throw it in the bin. All right, again, this is just like the last one. You could do this by quotient rule, but honestly, you'd be a fool if you did, because we could clean this up first. We could just divide every single term by the x. Divide this by x, divide that by x, divide that by x. And we'll get a simplified version. So this would be 3x to the 5th plus 4x cubed plus x. And so right away, we just end up with a much easier to differentiate expression. So this derivative will be 15x to the 4th, 12x squared, plus 1. And I guess the only big thing to point out is, remember, the original function g had this natural domain restriction that said x can't be 0. So I don't know, I don't think I'd hold you to it, I don't think I'd mark you down, but we really should be saying here that in this derivative of ours, x can't be 0, because you wouldn't know that without looking at it. You would have thought it would be perfectly fine to substitute in 0 here. We would just get 0 plus 1, we would get 1. But we know that the original function g is undefined at 0, which means the derivative can't be defined at 0. We have to inherit those domain restrictions. This is something I haven't been making a big deal about, so like I said, I won't hold you to it on the quiz, but it is definitely a big idea that you've already covered before in pre-calc, so you should understand it. Ask me about it tomorrow, or ask me about it later if you don't. I should also double check if we're factorable, but I don't think we are. We'd be looking at factors of 15 times 1. We'd be trying to get 12. We're just not going to get 12 because my choices are 1 and 15, 3 and 5. That's it. It's just that. So if I wanted a 16 here, we could have done it. If we wanted an 8, we could have done it. But that's not factorable. Moving on. Let's do 4. Okay. So 4 now is a quotient rule problem that we can't do it any other way. It just has to be quotient rule, so just bite the bullet and do it. Can't even rewrite anything first, so literally just dive right in. You're going to do g prime. Derivative of the numerator is simply 2, then you get an x squared plus 3, then you're going to subtract from that 2x plus 1, and the derivative of the bottom is 2x. And this will all be all over x squared plus 3 squared. So again, the derivative part, the differentiating, should be a piece of cake. It's the rewriting that gives me a little bit of nervousness, but take the 2, distribute it, you get a 2x squared plus 6. Now take the negative and distribute it, and then imagine distributing the 2x onto that too. So you'd have a minus 2 times 2 is minus 4x. Then you'd have a minus 1 times 2 is minus 2x. And again, I would strongly urge you to leave the denominator alone. And then just clean up the numerator. So I'm only seeing the 1 quadratic, so 2x squared. We've got the 2 linear terms that'll combine into a minus 6x. We've got the 1 constant plus 6. We can stick it on the end. And I'm sure you're all spotting the factor of 2. So we'll pop out a factor of 2, and that'll give us our final answer. So we have 2 times x squared minus 3x plus 3 all over x squared plus 3 squared. All right, and again, do check, because you never know, but can I factor this quadratic? I can't, because the only factors of 3 are 1 and 3, and you're not going to add them up to get a negative 3, so this blue answer is the end of the road. That's as clean as we could possibly make it. Now 6. Alright, so for 6, again, I guess. I don't know. I wonder if it's better. What's stopping me from just grabbing that guy, pulling him up into the numerator, and making his exponent negative? That's what we've been doing, right? So if you do that, could you then approach this problem like it was a product rule problem? You could. I just don't think it's better necessarily. I think either way is going to be just as good here. Honestly, I think we're better off avoiding the negative exponent. So I would leave it downstairs, and I'd go ahead and use quotient rule. And I think it's going to feel better if we do it that way than if we did it any other way. So without further ado, we're going to get f prime. Derivative of the numerator is just negative 2 times our denominator, which is e to the x. Subtract from that 1 minus 2x times the derivative of the bottom. Derivative of e to the x is e to the x. And then in the denominator, we'll do e to the x squared. All right. So upstairs we have negative 2e to the x. Then we'll distribute the negative and we'll distribute an e to the x onto this. So we'll get minus e to the x and then plus 2x e to the x. Okay, now technically e to the x squared, you could rewrite that as e to the 2x. But that seems a bad idea, because if you kind of plan ahead a little bit, you should probably see that a little ways down the road, we're going to be factoring an e to the x out of all these. And by the time we're done factoring out that e to the x, would have a negative 2 minus 1 plus 2x. Yeah. And so then if you had rewritten this as e to the 2x, then you may not notice, or you may forget, how this e to the x and this e to the 2x could be reduced, or if they even could be reduced. So this is a good point for me to remind you. E to the 2x, that was just e to the x squared. And expressed like that, e to the x squared, I think it's pretty obvious how these guys interact. It's that this e to the x will cancel one of these e to the x's, right? And so that whole e to the x cancels for us. And we can now clean up our numerator to where the 2x is going to come first. And it'll be minus 3. And that'll be getting divided by just 1 e to the x. Instead of e to the x squared, it'll just be the 1 e to the x. And that's definitely the best answer for us. So that's 6. And I think 8 is another one of these stupid table problems that I am very sick of at this point. But hopefully the fact that I'm sick of it means that you guys are getting good at it. So let's go ahead and start by finding a prime of t first. How about this time we don't mess with the 4 at all, we just leave it in there. And imagine doing our derivative. So the derivative of 4ht would be 4h prime t. And we'll multiply that by the denominator, which is f of t. Then we'll subtract the same 4, but h of t instead of h prime. And we're going to hit that with f prime of t. And then in the denominator, we'll get whatever f of t is. And we'll square it. Squaring the whole thing. Okay, so there's my derivative. You don't have to clean it up. Go ahead now and just jump to a prime of 1. And don't bother taking time even to plug the little 1's in there. Just go ahead and start evaluating. So this will be a 4 times h prime of 1, which is that 2. Then times an f, normal f giving negative 3. But this whole thing is just it's just 3 things multiplied together, and that's what I see here. The 4, then this derivative value, and then this function value, and it's just whatever. Okay, minus. Again, I've got a 4, and then a thing, and then a thing. And the two things are h of 1, which is 4, and f prime of 1, which is 6. And in the denominator, we've got f of t, so the negative 3 squared, And so there's our value of a prime of 1. We just clean this up now. So that's 8 and 3, that's 24, negative 24. Then minus 24 times 4. 424 is being 96. I'm going with 96. Denominator is positive 9, which means my numerator is 120, negative 120 over 9. And I do expect fractions reduced, so it should be pretty obvious that both of those are divisible by 3, and you now have negative 40 in the numerator, 3 in the denominator, and you can't go any farther than that. Is 40 thirds correct? Drum roll, please. It is. All right, great. So that means we can do B now. And then we can be done. Okay, so there's B. Put it right there. Get rid of the rest. Okay. Alright, and I'm running out of steam, so I'm going to go a little faster probably, but you're going to find me B prime of t first of all. You're going to do quotient rule on it. So you know you're going to have in your numerator this guy's derivative, which would be 3h prime of t. But then the derivative of the 2 is 0, so ignore that. Then multiply that by your denominator, f of t minus 1. And subtract, bring down the numerator, 3h of t minus 2. Multiply that by the derivative of the denominator, which seems to just be f prime of t. And then the denominator would be f prime, or f of t, no prime, minus 1, square the whole thing. There's the derivative, so now let's find b prime of 1. Okay, so that'll be 3 times h prime of 1, that's a 2. And then you'll multiply that by f of 1, which is negative 3, minus 1. Then a minus sign. Then a 3 times an h, which is 4, minus 2. F prime is giving 6. Okay, all over f prime is negative 3 minus 1. And we're going to square that. So, according to all this, it looks like I've got a 6 times a negative 4. And I'm going to subtract from that. 12 take away 2 is 10 times 6. All over negative 4 squared. So that's a negative 24 minus a 60 all over a positive 16, because of course that negative is getting squared too. So it's a positive 16. So that's, I think maybe I made a mistake here somewhere. Let's find out. That's negative 84 over 16. All right, assuming I'm right, chop those in half. Negative 42 over 8. Chop those in half again. Negative 21 over 4. I don't have a good feeling. I think I do. I think we're fine. Yeah, negative 21 over 4. I just don't feel like I'd seen that number before, but we're good to go. Hopefully this all is making sense now. Hopefully everything's making sense. Because our quiz is, I don't know, in your world it's probably Thursday, so our quiz is tomorrow. For me, it's still Wednesday. So Quiz Friday, come prepared. See me if you need help. Goodbye.